This web interface is meant to demonstrate the capability developed along the IONIO project to compute, for vessels with underdefined parameters, safe and optimal routes between any two locations in the Southern Adriatic and Northern Ionian Sea region, which is also termed SENI area in what follows. The web interface of the IONIO ship routing and safety decision support system is made up of three major parts. In the center, a geographical map centered on the SENI area. On the left, a menu for parameters insertion and interface control. At top, a banner with the help and parameters info buttons, useful for understanding the functioning of the interface and the meaning of the technical parameters. Upon a route computation request, the system displays on the map two routes between departure and arrival location. The geodetic route, in black, directly joins the two selected locations and does not consider safety restrictions on navigation. The optimal route, in red, keeps into account sea state forecast with the objective of minimizing navigation time and fulfilling safety requirements of the International Maritime Organization. In order to use the interface, the first step is to decide a departure, date and time. If no action is taken, this will be today at the time you first logged on the interface. Let us for instance take October 28th at 2 p.m. Secondly, you have to select a departure and an arrival location. This can be done most easily by clicking on the Capture Coordinate button. Then you click on the departure location and corresponding geographical coordinates appear in the mask in the left menu. You click again another point and the coordinates of arrival location are captured. In this example, we select Kalamata, Greece, as departure and Otranto, Italy, as arrival location. We see that this choice is confirmed by two blue stars appearing at these two locations. We now may want to modify the extent of so-called bounding box for route computation. Clicking on the Parameters Info button, a graphic explains what the bounding box is. It is suggested to enlarge the bounding box buffer by increasing the values of parameters delta lat up and down and delta lon left and right. This helps in computing an optimal route, especially in case there is a complex coastline between departure and arrival location. In this example, let us increase the delta lat down value to 0.50 degrees. Now, always staying in the left menu, we pass to Optimization Parameters section. If corresponding choice intentional speed reduction is valued 1, the system will allow the algorithm to voluntary decrease engine throttle for avoiding potential hazard to navigation. Instead, by setting intentional speed reduction to 0, engine throttle will always be kept at 100%. Then we have the Safety Parameters section. Here are the parameters for checking the intact stability of the vessels. The exact meaning of each of these parameters can be found by clicking on the Parameters Info button. Therefore, also a useful bibliographic reference is linked. The values 1 or 0 respectively mean safety check switched on or switched off. For instance, let us set 0, 1, 0 in this mask. This way, the system will just check for pure loss stability. Finally, we have the Ship Information section with vessel propulsion parameters and principal particulars. For instance, we might decide to change engine power to 550 horsepower, cruise speed to 12 knots, hull length to 20 meters, beam or width to 6 meters, draw to 2 meters, and vessel's natural roll period to 5 seconds. Now, everything is ready for creating a short command string to be used for requesting a route computation to the IONIO data center. Just click on the Create Submission String. A pop-up containing such string opens. The text can be easily copied to the clipboard and then pasted into the body of a mail message to be sent to the IONIO data center. Simply write IONIO route request in the subject and get the mail recipient address from the help button on the web interface. The data center will reply by attaching two files with JSON extension. Download them to your computer and then upload them onto the interface. The file with GDT in its file name must be loaded after clicking on the geodetic button. The other file must be loaded after clicking on the optimal button. Now, click on the rendering. Two routes get displayed on the map. The one with the black circle is the geodetic route. The one with the red circles is the optimal route. It is possible to plan the map and zoom in or out. In this case, we see that the optimal route significantly deviates from the geodetic one, moving more inshore and avoiding rough sea conditions. It is further possible to inspect individual waypoints on the routes. For instance, this waypoint, numbered 92 in the geodetic route, is reached on October 29th at 11:23. At that time, the vessel has been sailing for 214 nautical miles and is advancing at a speed of 10.5 knots, with engine throttle set at the maximum value, encountering a new wave crest more or less every 14 seconds, and wave significant height is 80 centimeters. Furthermore, extra information can be accessed through the Plots section, which is activated by clicking on the P mark on the right-hand margin of the map. Here you can visualize the full voyage plan, containing for each waypoint the time of the passage, the distance covered since departure, engine throttle, sustained ship speed, encounter wave period, and significant wave height. There are two voyage plans, one for the geodetic and one for the optimal route. The section along route plots allows displaying the time evolution of relevant parameters along each of the routes. The ship speed button opens a pop-up with two panels. The upper panel contains information on the optimal route, while the lower panel on the geodetic route. It is apparent that along the optimal route, on the average, a higher ship speed is maintained with respect to the geodetic route. This allows the optimal route to minimize sailing time. The ship course is plotted using the convention that 0 degrees means northbound navigation, 90-degree eastbound, and so on. For instance, the value 210 we see here is a south-southwestern bound navigation, prevailing in the initial part of both routes in this case, while the value 330 is a north-northwestern bound navigation, which in this case is the dominant ship course at later times. Engine throttle. As in this case, we left the default value for what concerns the optimization options. We see that there are portions of the route whereby the throttle gets reduced to 55, 85, or 70%. Such voluntary reduction allows the vessel avoiding diversions, which would cause an extra cost in terms of total sailing time. By clicking on the Significant Wave High button, we see that along the optimal route, significant wave high is anyhow below 90 centimeters, while waves can be as high as 130 centimeters along the geodetic route. It is this avoidance of rougher sea that enables the optimal route to be faster than the geodetic route. Encounter wave period is a time for vessel to encounter two successive wave crests. It has an effect on ship stability, as a resonance rolling may activate if such period matches the ship's natural roll period or its half. Finally, there is a danger flags section. They show unsafety indexes along the geodetic route. 1 means danger, 0 means no danger. For instance, the Pure Loss Stat button shows that in the case the geodetic route may lead to pure loss of stability at several waypoints. For further information on the use of the web interface of IONIO ship routing and safety decision support system, please use the Help and Parameters info buttons. Thank you and have a nice experience with this system.